everybody, welcome to my presentation on identifying code changes for architecture decay via a metric forest structure. I'm Yuyun Zhang. I will introduce our work from 5 aspects. Firstly, I will introduce our motivation. During software evolution, developers may choose suboptimal design decisions to add new requirements or other activities. After continuous iteration, these code changes will technical debt and architectural debt, causing the architecture to decay. Architectural erosion detection will help developers resolve problems in time, improve software maintainability, and reduce the interest expense for debt payoff. There is currently a lot of maintainability-related works, but there still exists a gap between the implementation level metrics and architecture level metrics. So, how to bridge this gap? We can connect the logic relationship between implementation level metrics and architecture level metrics. This gap will be filled. It will help guide developers in making effective code changes toward a better architecture level measurement. Next is our method. We propose the DB2023 to identify potential code changes responsible for the architecture decay during software evolution. This is the method overview. The difference is that the key of DB2023 is the metric forest structure, which organizes the multi-grid metrics in a hierarchical structure. This is the metric forest structure we have constructed. In this structure, 77 metrics are integrated in total, including 38 metrics from the CK suite, 10 metrics from the Q-mode suite, and 29 metrics from other related works. First, we collect these 77 metrics. Next, we list the collected metrics hierarchically in terms of the measurement granularity and links these metrics in terms of maintainability sub-features, thus forming a forest structure. These metrics can be classified into 3 sides, namely functionality, modularity, and evolvability. And the metrics in each side are organized hierarchically. Present module, class, and method levels. The module level metrics are located at the top level, followed by the class level metrics and the method level metrics. After that, we construct a link for a pair of metrics across different lines. The forest structure serves as a knowledge base to organize scattered and diverse metrics. It can help realize how implementation level code changes would propagate inside and across modules, subsequently influencing architecture level maintainability. This is our design problem detection rules, which are divided into 2 groups, namely detection coupling problem and cohesion problem. Taking the rule set for detecting coupling problem as an example, precondition is requisite of the 3 rules. Initially detecting a set of classes with an increase of dependency on another module. The Rule 1, Rule 2, and Rule 3 identify the implementation level changes responsible for tight coupling. With these detection rules, we can identify which method-level changes made in software version would cause software maintainability issues. The third part is our experiment. We collected 61 microservice projects, 5 Android-based projects, and 7 projects studied by related works. Finally, our experimental subjects include 73 projects. Our ground truth includes 3 metrics. We conducted maintainability measurement experiments in 73 projects. This is the result. We can observe that score range from 0.4 to 0.8, and 43% projects present maintainability levels lower than the average level. This is our architecture decay detection results. We validated the maintenance cost of detection results on 94 versions. MCA denotes the results of the average value on problematic entities. MCB denotes the results of the average value on non-problematic entities. P denotes the rate of MCA to MCB. If the value of P is bigger than 1, it means that the problematic code reported by DBMIT indeed incurred more maintenance efforts. From the results, we can observe that the maintenance cost of problematic entities indicated by DBMIT is higher than that of non-problematic entities. We also presented a case study. This case used Lineage OS as an example. This is the result of population distribution. And this is the growth curve. Lineage 17.1 achieves a score of 0.6634, ranking in the top 45% among all projects. It indicates that the maintainability of Lineage OS 17.1 surpasses the population average level. It can be seen that the code modifications made in Lineage OS 17.1 lead to severe quality degradation compared to other versions. At this point, it requires the design problem detection to identify how code changes have incurred this volatile fluctuation. Stats is the module with the most severe issue. We further detected problematic classes in the reported module of stats via class-level metrics such as CBC, EDCC, and cfanout. Next, we continued to pinpoint method-level code changes to explain the issue of the reported stats companion series class. These two methods are the most severe methods. The case demonstrates that our DBMIT is able to pinpoint implementation level changes from a coarse grain to a fine grain. We also design and implement a web-based tool to measure, detect, and visualize to soft architecture presenting potential code changes responsible for the erosion. There are the implement interfaces. Our work has two implications. Filling this gap helps address requirements of comprehensibility, interpretability, and indicatability. The method can pinpoint the code changes responsible for maintenance difficulty. There are 4 threats to validity. The first threat is the reliability of the metrics we used. The second is about the forest structure that related metrics together in a set of trees. Another possible threat is the limited number of rules defined in DBMT. Last but not least, experimental might produce inconsistent observations when applied to diverse projects. In January, our work makes contributions as follows. We propose the DBMT. The key of DBMT is a metric forest structure that bridges the gap between architecture-level metrics and implementation-level metrics. We implement a web-based tool named MicroEvaluator that integrates dependency extraction, software reconstruction, maintainability measurement, decay detection, and visualization. We contribute the metric forest structure with a knowledge base and a dataset for continuous research. That's all my presentation. Thanks. So, have any questions?